The universe is a tapestry of secrets, woven together by threads of light and darkness that stretch across unimaginable distances. Hidden within its vast expanse lies a mysterious structure, a cosmic web, where galaxies cluster like jewels on an invisible net. But this web isn't just a random arrangement. It holds patterns, intricate and enigmatic, that whisper the universe's deepest truths. These 28 patterns aren't just shapes, they're keys to understanding how the cosmos came to be, how it evolves, and perhaps even where it's headed. What if I told you that these patterns could reveal the origins of everything we see, or that they might hold clues to phenomena we can't yet explain? Today, we're diving into the heart of these mysteries, uncovering what the cosmic web can teach us about the universe's grand design. From the birth of galaxies to the forces that shape the void, each pattern tells a story, one that challenges what we think we know and invites us to see the cosmos in a whole new light. So, what do these patterns reveal about the universe's origins? How do they influence the birth and death of stars or the very fabric of space itself? As we explore these 28 enigmatic structures, prepare to be amazed because the cosmic web is more than a map. It's a doorway to the universe's most profound secrets. And the first pattern, it's a glimpse into one of the most astonishing phenomena in the cosmos. Picture this, a colossal structure so vast that it defies comprehension, a wall not of stone or brick, but of galaxies, thousands of them, stretching across the cosmos like beads on an infinite string. This is the Great Wall of Galaxies, one of the most awe-inspiring patterns in the cosmic web. Discovered in the late 1980s, this immense filament of galaxies sent shockwaves through the world of astronomy. Up until then, scientists believed the universe was relatively uniform, with matter evenly distributed. But the Great Wall shattered that notion, revealing a universe far more intricate and clumpy than anyone had imagined. Imagine if you could shrink the universe down to the size of a football field. The Great Wall would stretch from one end to the other, a towering chain of galaxies bound together by the invisible threads of gravity. It's not just big, it's monumental, one of the largest structures ever observed. But what makes it truly fascinating isn't just its size, it's what it tells us about the universe's architecture. This cosmic tapestry, woven over billions of years, shows us how gravity pulls matter together, creating these vast, interconnected networks. The discovery of the Great Wall didn't just challenge existing theories, it reshaped them. It forced scientists to rethink how galaxies form and cluster, offering a glimpse into the universe's large-scale structure. And yet, as enormous as it is, the Great Wall is just one thread in an even grander design. What other patterns lie hidden in the cosmic web, waiting to be uncovered? What secrets do they hold about the forces that shape the cosmos? As we move deeper into this cosmic labyrinth, the next pattern promises to reveal even more about the universe's mysterious, interconnected nature. Now, shift your gaze from the Great Wall's dazzling array of galaxies to a place that's almost the exact opposite, a region so empty, so profoundly devoid of matter, that it feels like the universe forgot to fill it in. This is the Boots Void, a cosmic anomaly that stretches an astonishing 330 million light-years across. To put that into perspective, if the Milky Way were a single grain of sand, the Boots Void would be a vast, empty beach, silent, dark, and eerily still. Astronomers often refer to this region as a cosmic desert, and it's easy to see why. While most of the universe is filled with galaxies, stars, and swirling clouds of gas, the Boots Void is almost entirely blank. Only a handful of galaxies dot this immense expanse, making it one of the emptiest places ever discovered. But how does something like this even exist? And what does it tell us about the universe's structure? One theory suggests that the Boots Void might be the result of dark energy. the mysterious force driving the universe's accelerated expansion. Some scientists believe that dark energy could have pushed matter away from this region, leaving behind a void so vast it defies our understanding of cosmic distribution. Others propose that it's the remnants of smaller voids merging together over billions of years, creating this colossal emptiness. But the Boots void isn't just a scientific curiosity, it's a challenge to our assumptions about the universe. For decades, astronomers believed that matter was spread relatively evenly across space. The discovery of this void turned that idea on its head, showing that the cosmos is far more uneven and unpredictable than we thought. It's a reminder that the universe still holds secrets we're only beginning to uncover. And yet, as empty as the Boots void is, it's not the only extreme in the cosmic web. Just as there are deserts, there are also jungles, places where galaxies gather in such dense clusters that they seem to defy gravity itself. What happens when we shift our focus from the emptiness of the Boots void to the bustling, crowded neighborhoods of the universe? The next pattern will take us there, into the heart of a galaxy cluster so dense, it's like a cosmic metropolis. From the eerie emptiness of the Boots void, let's turn our attention to a place where the universe seems to have gone all in a region so densely packed with galaxies that it redefines our understanding of scale. Meet the Hercules-Corona Borealis Great Wall, a structure so massive that it challenges everything we thought we knew about the cosmos. Discovered in 2013, this colossal formation stretches an astonishing 10 billion light-years across, making it one of the largest known structures in the universe. To put that into perspective, if the Milky Way were the size of a marble, the Hercules-Corona Borealis Great Wall would span the length of several football fields. What makes this structure so extraordinary isn't just its size, it's what it means for our understanding of the universe. For centuries, scientists have operated under the cosmological principle, the idea that, on a large enough scale, the universe is uniform and looks the same in every direction. But the Hercules-Corona Borealis Great Wall throws a wrench into that assumption. Here, galaxies aren't just scattered randomly, they're concentrated in a way that suggests the universe might not be as evenly distributed as we once believed. Think of it like this: if the universe were a loaf of bread, we'd expect the raisins representing galaxies to be spread out more or less evenly. But the Hercules-Corona Borealis Great Wall is like finding a massive cluster of raisins all clumped together in one corner of the loaf. This discovery has forced astronomers to rethink the rules of cosmic architecture. Could there be even larger structures waiting to be discovered? And if so, what does that mean for our theories about how the universe evolved? The implications are profound. If structures like this exist, they might hint at forces or processes we don't yet understand. Some scientists speculate that the Hercules-Corona Borealis Great Wall could be evidence of ancient cosmic events, like the collision of superclusters billions of years ago. Others suggest it might be connected to the mysterious influence of dark matter, the invisible substance that makes up most of the universe's mass. But here's the thing, as mind-boggling as this structure is, it's just one piece of the cosmic puzzle. The universe is full of surprises, and not all of them are about size or scale. Sometimes the most intriguing patterns are those that challenge our understanding of time itself. What happens when we look at the cosmic web not as a snapshot of the present, but as a record of the past? The next pattern will take us there, into a realm where the universe's history is written in light. The cosmic web is a masterpiece of complexity, and within its vast expanse lies another breathtaking marvel, the Sloan Great Wall. Discovered in the early 2000s through the Sloan Digital Sky Survey, this colossal filament of galaxies stretches over 1.4 billion light-years, making it one of the largest structures ever observed. Imagine a river of stars and galaxies flowing through the void, connected by the invisible threads of gravity. This is the Sloan Great Wall, a testament to the universe's intricate design and a key to unlocking its deepest mysteries. What makes this structure so remarkable isn't just its sheer size, but the role it plays in helping us map the cosmic web. By studying the Sloan Great Wall, astronomers have gained invaluable insights into how galaxies form and cluster together. It's like looking at a blueprint of the universe's architecture, revealing the delicate balance between gravity's pull and dark energy's push. Each galaxy within this wall is like a brushstroke on a cosmic canvas, contributing to a picture of how the universe has evolved over billions of years. But the Sloan Great Wall isn't just a static snapshot. It's a dynamic record of the universe's history. Its intricate structure tells a story of collisions, mergers, and interactions, offering clues about the forces that shape the cosmos. For instance, the way galaxies are distributed along this filament suggests that they didn't form randomly. Instead, they were drawn together by the gravitational pull of dark matter, the invisible scaffolding that holds the universe together. Speaking of dark matter, its role in shaping structures like the Sloan Great Wall is nothing short of extraordinary. While we can't see it directly, its influence is everywhere, weaving the cosmic web into the patterns we observe today. But how exactly does this mysterious substance work, and what other secrets does it hold about the universe's evolution? As we prepare to dive deeper into the cosmic web, the next pattern will take us into the shadowy realm of dark matter. It's a journey into the unseen, where the universe's hidden forces come to life, shaping everything from the tiniest galaxies to the grandest structures. What lies beyond the visible? What role does dark matter play in the cosmic dance? The answers might just change how we see the universe forever. The cosmic web is more than just a collection of galaxies and stars. It's a network held together by something we can't even see. Enter dark matter, the invisible architect of the universe. This mysterious substance doesn't emit light, absorb it, or interact with electromagnetic forces, yet its presence is felt everywhere. Dark matter forms the backbone of the cosmic web, its gravitational pull weaving vast filaments that stretch across the cosmos like invisible threads in a grand tapestry. These filaments are the scaffolding upon which galaxies and clusters are built, guiding the flow of matter and shaping the universe as we know it. Picture this, dark matter filaments as the hidden highways of the cosmos. Imagine them as rivers of gravity flowing silently through the void, drawing galaxies and gas into their currents. Where these filaments intersect, they create dense nodes, cosmic hubs where galaxies cluster together in bustling metropolises. Between them, the voids stretch out, vast and empty, like the quiet spaces between cities. It's a delicate dance, one where dark matter plays the lead role, orchestrating the distribution of everything we see. But how do we know dark matter is there if we can't see it? The answer lies in its gravitational effects. Astronomers observe how galaxies move and how light bends around massive structures, and these observations point to the presence of something unseen. Dark matter's gravitational pull is so powerful that it warps the fabric of space itself, creating a cosmic map that scientists can trace through its influence. Without dark matter, the universe as we know it wouldn't exist. Galaxies wouldn't form, and the cosmic web would collapse into chaos. Yet, for all its importance, dark matter remains one of the greatest mysteries in modern science. What exactly is it made of? How does it interact with the visible universe? These questions drive astronomers to study the cosmic web in ever greater detail, searching for clues hidden in the patterns of galaxies and gas. And speaking of gas, that brings us to the next piece of the puzzle. While dark matter forms the skeleton of the cosmic web, ordinary matter, the stuff we can see, fills in the details. Galaxies, stars, and swirling clouds of gas are all part of the story, but they move to the rhythm set by dark matter's invisible hand. What happens when these two forces, dark and visible, come together? The next pattern will take us into the heart of this interplay, revealing how the seen and the unseen shape the universe in ways we're only beginning to understand. The story of the cosmic web doesn't begin with galaxies or dark matter. It starts with a faint glow, a whisper from the dawn of time itself. This is the cosmic microwave background, or CMB, a relic of the universe's infancy and one of the most profound discoveries in modern cosmology. Think of it as a snapshot frozen in time, capturing the universe just 380,000 years after the Big Bang. Back then, the cosmos was a seething, opaque soup of particles and energy. But as it expanded and cooled, light broke free, and that light has been traveling through space ever since, carrying with it the secrets of the universe's earliest moments. What makes the CMB so extraordinary isn't just its age, it's the story it tells. When we look at it today, we're not just seeing a uniform glow, we're seeing tiny ripples, fluctuations in temperature that are barely a fraction of a degree. These imperfections might seem insignificant, but they're the seeds of everything we see in the universe today. They're the first hints of structure, the subtle variations in density that gravity would later amplify into galaxies, clusters, and the vast filaments of the cosmic web. Imagine the CMB as a canvas painted with the faintest brushstrokes. Each fluctuation is like a tiny dot, a starting point for the universe's grand design. Over billions of years, gravity worked its magic, pulling matter into denser regions and leaving voids in between. What began as microscopic ripples grew into the sprawling network of galaxies and clusters we observe today. The CMB is the foundation, the blueprint from which the cosmic web was built. But the CMB isn't just a map of the universe's structure, it's also a key piece of evidence for the Big Bang theory. The discovery of this ancient light in the 1960s was a game-changer, confirming that the universe had a hot, dense beginning. It's like finding a photograph of the cosmos as a baby, a glimpse into its earliest moments that helps us piece together how it grew into the vast, complex place we know today. And yet, the story doesn't end there. The CMB is just the beginning, the first chapter in a tale that spans billions of years. Those tiny fluctuations didn't stay small. They evolved, shaped by gravity, dark matter, and the mysterious force of dark energy. How did these ripples grow into the colossal structures we see today? What forces guided their transformation? The next pattern will take us deeper into this journey, exploring how the universe's early whispers became the cosmic symphony we now observe. The universe didn't start with sprawling galaxies or vast cosmic walls. It began with the tiniest of whispers. Those faint ripples in the cosmic microwave background, the ones we talked about earlier, were more than just remnants of the Big Bang. They were the seeds of everything we see today. Over billions of years, these minuscule fluctuations grew, driven by one of the most fundamental forces in the cosmos, gravity. Imagine the early universe as a quiet pond. Drop a single pebble and ripples spread outward, small at first but growing stronger as they move. Those initial ripples in the cosmic pond were the density variations in the early universe. Gravity acted like an invisible hand, pulling matter into the denser regions, while leaving the thinner areas to expand into voids. Over time, these clumps of matter grew larger and more complex, eventually forming galaxies, clusters, and the intricate filaments of the cosmic web. But gravity wasn't working alone. Enter dark energy, the mysterious force that's been accelerating the expansion of the universe. Picture dark energy as a cosmic wind, gently but persistently pushing space itself apart. While gravity pulls matter together, dark energy works in opposition, stretching the fabric of the universe. This tug of war between gravity and dark energy has shaped the cosmic web in profound ways. Without dark energy, the universe might have collapsed back in on itself. Instead, it has continued to expand, creating the vast, intricate structures we observe today. So, how did this interplay between gravity and dark energy lead to the growth of cosmic structures? Think of it like building a sandcastle. Gravity is the sculptor, shaping the sand into towers and walls, while dark energy is the tide, slowly but surely washing away the edges, making room for new formations. Together, they've created a universe that's both structured and dynamic, where galaxies cluster into superclusters and voids stretch between them like cosmic deserts. And speaking of superclusters, these colossal gatherings of galaxies are some of the most awe-inspiring features of the cosmic web. They're not just random clusters, they're the intersections of the universe's largest filaments, where gravity has pulled together thousands of galaxies into bustling cosmic cities. But what exactly makes superclusters so special? How do they fit into the grand design of the universe? That's where we're headed next, into the heart of these galactic metropolises, where the story of the cosmic web becomes even more fascinating. Within the vast expanse of the cosmic web, there's a structure so immense that it reshaped our understanding of where we live in the universe. This is the Laniakea Supercluster, a sprawling network of galaxies that includes our very own Milky Way. The name Laniakea comes from Hawaiian words meaning immense heaven, and it's a fitting title for a structure that spans over 500 million light-years. Discovered in 2014 by a team of astronomers using advanced mapping techniques, Laniakea isn't just a random collection of galaxies. It's a gravitational metropolis, a place where galaxies are drawn together by the invisible pull of dark matter, moving in unison like leaves caught in a cosmic river. Think of Laniakea as a galactic superhighway, with our Milky Way as just one car among countless others. At its heart lies the Great Attractor, a mysterious region of space with such immense gravitational pull that it's drawing galaxies ours included toward it at incredible speeds. This supercluster isn't just a static structure, it's dynamic, alive with motion, as galaxies flow along the filaments of the cosmic web toward its gravitational core. What makes Laniakea so significant isn't just its size, it's how it redefines our place in the universe. Before its discovery, astronomers thought of superclusters as isolated islands of galaxies. Laniakea showed us that these islands are connected, part of a larger, interconnected network that shapes the movement and evolution of galaxies. It's like realizing that your hometown isn't just a small village but part of a bustling, interconnected city. But Laniakea isn't just a cosmic landmark, it's also a window into the forces that govern the universe. By studying how galaxies move within this supercluster, scientists can better understand the role of dark matter and gravity in shaping the cosmic web. It's a reminder that even on the grandest scales, the universe is governed by the same fundamental forces we observe here on Earth. As we marvel at the scale and complexity of Laniakea, it's worth asking, what lies beyond its borders? The cosmic web isn't just made of superclusters, it's also defined by the vast, empty spaces between them. These voids, regions of near total emptiness, are just as important as the clusters themselves. What secrets do these cosmic deserts hold, and how do they shape the universe's grand design? The next pattern will take us there, into the quiet, mysterious spaces between the stars. In the vast tapestry of the cosmic web, where galaxies cluster and filaments stretch across the void, there are places that seem almost otherworldly in their emptiness. Enter the Eridanus Supervoid, a region so vast and so empty that it defies our understanding of space itself. Spanning an astonishing 1.8 billion light-years, this supervoid is one of the largest known structures in the universe. But what makes it truly extraordinary isn't just its size, it's the mystery that lies at its heart. A cold spot in the cosmic microwave background, the faint afterglow of the Big Bang. This cold spot, first detected by satellites in the early 2000s, is a puzzling anomaly. While the CMB is remarkably uniform, this region is noticeably cooler, as if a piece of the universe's early history had been erased or altered. Scientists have proposed several theories to explain this phenomenon, and one of the most intriguing suggests that the Eridanus supervoid might be the result of a collision with another universe. Imagine for a moment the idea of multiple universes brushing against each other, leaving behind a cosmic fingerprint in the form of a cold spot. It's a theory that pushes the boundaries of our understanding and challenges everything we thought we knew about the cosmos. But the Eridanus supervoid isn't just a scientific curiosity, it's also a window into the nature of cosmic voids. These vast, empty regions play a crucial role in shaping the universe. They're not just blank spaces, they're part of the cosmic web's intricate balance, the quiet counterpoints to the bustling galaxy clusters and filaments. Without voids, the universe's structure would be profoundly different. The Eridanus supervoid, with its eerie emptiness and mysterious cold spot, reminds us that even the absence of matter can tell a story, one that's still being written. As we ponder the implications of this supervoid, it's worth asking, what other forces are at work in the cosmic web? What role do the brightest and most energetic objects in the universe play in illuminating its structure? The next pattern will take us into the heart of this question, exploring how quasars, the blazing beacons of the cosmos, help us map the invisible threads that bind the universe together. Amid the sprawling expanse of the cosmic web, there are objects so luminous, so powerful, that they outshine entire galaxies. These are quasars' cosmic lighthouses blazing across the universe, guiding astronomers through the darkest corners of space. Born from the hearts of ancient galaxies, quasars are fueled by supermassive black holes, consuming matter at such a staggering rate that they emit light brighter than 1 trillion suns. But their brilliance isn't just for show. It's a tool helping scientists map the intricate structure of the cosmic web in ways that would otherwise be impossible. Imagine a quasar as a flashlight in a vast, dark forest. Its intense light pierces through the cosmic fog, illuminating the gas and galaxies that lie between us and the quasar. As this light travels billions of light years to reach us, it passes through the filaments of the cosmic web, leaving behind a kind of fingerprint. By analyzing the light from quasars, astronomers can detect the presence of gas clouds, measure their density, and even trace the distribution of galaxies along the filaments. It's like using a cosmic X-ray to reveal the hidden skeleton of the universe. But quasars don't just help us see the cosmic web, they also tell us about its evolution. Because quasars are so distant, their light has been traveling for billions of years, giving us a glimpse into the universe's younger days. By studying quasars at different distances, scientists can piece together how the cosmic web has changed over time, from its infancy to the sprawling network we observe today. What makes quasars even more fascinating is their ability to reveal the invisible. Many of the gas clouds they illuminate are too faint to be seen directly, yet their presence is crucial to understanding how galaxies form and grow. These clouds are the raw materials of stars and planets, the building blocks of the universe itself. Without quasars, we'd be blind to this hidden reservoir of cosmic potential. As we marvel at the brilliance of quasars, it's worth considering how they fit into the larger picture of the cosmic web. They're not just beacons of light, they're storytellers, revealing the intricate connections between galaxies, gas, and the invisible threads of dark matter. But what happens when galaxies come together in massive clusters, forming the densest regions of the cosmic web? How do these clusters shape the universe around them? The next pattern will take us into the heart of these galactic gatherings, where the story of the cosmic web becomes even more dynamic and profound. Zooming in from the brilliant lighthouses of quasars, let's turn our attention to the bustling hubs of the cosmic web galaxy clusters. These colossal gatherings of galaxies are more than just random collections. They're the nodes where the universe's largest filaments intersect, forming the backbone of the cosmic web. Picture the cosmic web as a vast network of highways, with galaxy clusters as the major cities where these routes converge, and one of the most striking examples of these cosmic metropolises. The Coma Cluster, a dense swarm of over 1,000 galaxies located about 320 million light-years away. Galaxy clusters like Coma are more than just impressive in size, they're gravitational anchors, holding together the intricate structure of the cosmic web. Where filaments cross, the pull of gravity intensifies, drawing in galaxies, gas, and dark matter to form these massive clusters. It's like a cosmic crossroads where the threads of the universe come together to create something far greater than the sum of their parts. The Coma Cluster, for instance, is so massive that its gravitational influence shapes the surrounding regions, pulling in galaxies and gas from millions of light-years away. But galaxy clusters aren't just passive collections of matter. They're dynamic, evolving systems where galaxies collide, merge, and interact in a cosmic dance. Within the Coma Cluster, galaxies move at incredible speeds, sometimes crashing into one another in spectacular displays of cosmic fireworks. These collisions can trigger bursts of star formation, igniting new stars and reshaping the galaxies involved. Over time, the cluster becomes a melting pot of galactic evolution, offering a glimpse into how the universe's largest structures grow and change. What makes galaxy clusters especially fascinating is their role as laboratories for studying the universe's fundamental forces. The immense gravity of these clusters bends light, a phenomenon known as gravitational lensing, which allows astronomers to peer even deeper into the cosmos. By observing how light warps around clusters like Coma, scientists can map the distribution of dark matter, shedding light on its mysterious properties. And yet, galaxy clusters are only part of the story. While they dominate the intersections of the cosmic web, the filaments themselves are filled with something equally important: gas. Billions of degrees hot and invisible to the naked eye, this gas flows through the cosmic web, feeding galaxies and driving their evolution. So, what role does this invisible medium play in shaping the universe, and how does it connect the vast structures we've explored so far? The next pattern will take us into the hidden rivers of the cosmos, where the story of the cosmic web continues to unfold. As we journey deeper into the cosmic web, we encounter a hidden river flowing through the vast emptiness of space, one that's invisible to our eyes but crucial to the universe's story. This is the warm, hot intergalactic medium, or WIM, a diffuse, superheated gas that fills the spaces between galaxies. Though it sounds like something out of a science fiction novel, the WIM is very real, and it holds a surprising secret. It contains most of the universe's ordinary matter. That's right. While stars, planets, and galaxies get all the attention, the majority of the stuff we're made of is actually floating in this ethereal, intergalactic fog. So, what exactly is the WIM? Imagine it as a cosmic ocean, filled with gas so hot that it glows faintly in X-rays. This gas isn't clumped together like the clouds we see in galaxies. Instead, it's spread out in a thin, nearly invisible web that connects the universe's largest structures. It's the glue that binds the cosmic web together, flowing along the filaments and pooling in the voids, shaping the environment in which galaxies grow and evolve. But the WIM isn't just a passive backdrop, it's a dynamic player in the cosmic drama. This gas serves as the raw material for galaxy formation, providing the fuel for new stars and planets. As galaxies move through the cosmic web, they sweep up this gas, pulling it into their gravitational embrace and igniting the processes that lead to star formation. Without the WIM, galaxies would run out of fuel, and the universe as we know it would grind to a halt. Yet, for all its importance, the WIM is incredibly difficult to study. Its faint glow can only be detected by the most advanced telescopes, and even then, it's like trying to spot a candle flickering in a foggy forest. Scientists have spent decades piecing together its properties, using clues from the light of distant quasars and the faint X-rays it emits. What they've discovered is a complex, ever-changing medium that plays a vital role in the universe's evolution. And as we begin to unravel the mysteries of the WIM, another force emerges from the shadows, one that's just as invisible but equally powerful. Magnetic fields, though often overlooked, are thought to weave through the cosmic web, shaping the flow of gas and influencing the formation of galaxies. How do these invisible lines of force interact with the WIM, and what role do they play in the universe's grand design? That's where we're headed next, into the hidden currents of the cosmic web, where magnetism and matter collide in ways we're only beginning to understand. Hidden within the cosmic web, an invisible force weaves through the vast expanse of space, shaping the universe in ways we're only beginning to understand. These are cosmic magnetic fields, threads of magnetism that stretch across galaxies, filaments, and voids, influencing the flow of matter and the birth of stars. Though we can't see them directly, their effects are everywhere, from the swirling arms of galaxies to the delicate filaments that connect the universe's largest structures. Think of cosmic magnetic fields like the invisible currents in a river. Just as water flows in specific directions, guided by the shape of the riverbed, gas and dust in the universe are steered by these magnetic lines. They act as cosmic highways, channeling material along the filaments of the cosmic web and into the hearts of galaxies. Without them, the universe would lack the structure and order we see today. But how exactly do these fields form, and what role do they play in shaping the cosmos? One theory suggests that cosmic magnetic fields might have been born in the early universe, sparked by the turbulent motions of particles and energy in the aftermath of the Big Bang. Over billions of years, these fields grew stronger, stretching and twisting as galaxies formed and evolved. They're not just passive observers of cosmic events, they're active participants, regulating the flow of gas and influencing how stars are born. For instance, in regions where magnetic fields are strong, they can slow down the collapse of gas clouds, delaying star formation. In other areas, they might channel gas into dense knots, triggering bursts of star birth. But magnetic fields don't just shape galaxies, they also connect them. Along the filaments of the cosmic web, these fields stretch like invisible bridges, linking clusters and galaxies across vast distances. They're the unseen threads that bind the universe together, creating a network of influence that spans billions of light years. And while we can't see them, we can detect their effects through the polarization of light or the alignment of cosmic particles, giving us a glimpse into their hidden power. As we unravel the mysteries of cosmic magnetic fields, another force emerges from the shadows, one that's even more enigmatic and powerful. Black holes, the universe's ultimate cosmic engines, play a crucial role in shaping the cosmic web. How do these gravitational giants influence the structure of the universe? And what happens when their immense power collides with the delicate filaments of the cosmic web? The next pattern will take us into the heart of this question, exploring the profound impact of black holes on the universe's grand design. At the heart of nearly every galaxy, including our own Milky Way, lies a cosmic giant, a supermassive black hole. These gravitational behemoths, millions or even billions of times more massive than the Sun, are more than just voracious devourers of matter. They are architects of the cosmic web, shaping the universe on the grandest scales. From regulating star formation to influencing the flow of gas across galaxies, supermassive black holes are central players in the story of the cosmos. Take Sagittarius A, the supermassive black hole at the center of the Milky Way. While it may seem like a silent sentinel, its influence stretches far beyond its immediate surroundings. As matter spirals toward the black hole, it heats up, emitting immense amounts of energy in the form of radiation and powerful jets. These jets can stretch thousands of light years, carving through the interstellar medium and shaping the environment around them. But here's the twist: while black holes are famous for consuming matter, they also give back. The energy they release can heat up surrounding gas, preventing it from cooling and collapsing into new stars. This process, known as feedback, acts as a cosmic thermostat, regulating star formation and ensuring galaxies don't grow too quickly or burn out too soon. But the influence of supermassive black holes doesn't stop at the edges of their host galaxies. They also play a role in connecting the cosmic web. When black holes in different galaxies grow and merge, they create ripples in space-time called gravitational waves. These waves carry energy across the universe, subtly influencing the distribution of matter and reinforcing the filaments that make up the cosmic web. It's a cosmic dance where the most destructive forces also serve as creators, shaping the universe in ways we're only beginning to understand. What's even more fascinating is how supermassive black holes interact with their surroundings. In galaxy clusters, for example, the combined gravity of hundreds of galaxies can funnel gas toward the central black hole, feeding it and triggering powerful outbursts. These outbursts can push gas out of the cluster, preventing it from forming new stars and shaping the cluster's evolution over billions of years. It's a delicate balance, one where black holes act as both destroyers and regulators, maintaining the cosmic web's intricate structure. As we marvel at the immense power of supermassive black holes, it's worth considering what other forces shape the cosmic web. Beyond gravity and magnetism, there's another invisible player: cosmic rays. These high-energy particles, racing through space at nearly the speed of light, carry energy and influence the gas that fills the cosmic web. How do these cosmic messengers fit into the universe's grand design? And what secrets do they hold about the forces that shape the cosmos? The next pattern will take us into the high-energy realm of cosmic rays, where the story of the cosmic web becomes even more dynamic and surprising. As we venture further into the cosmic web, we encounter a phenomenon that's as exhilarating as it is elusive: cosmic rays. These high-energy particles, racing through space at nearly the speed of light, are the universe's invisible messengers, carrying secrets about the forces that shape galaxies and the filaments connecting them. Born from some of the most violent events in the cosmos: supernova explosions, colliding stars, and the jets of supermassive black holes, cosmic rays are more than just travelers. They're active participants in the cosmic web's intricate dance, influencing everything from star formation to the flow of gas between galaxies. Picture cosmic rays as tiny, hypercharged bullets, zipping through the universe with enough energy to illuminate the darkest corners of space. When they collide with gas clouds or magnetic fields, they can trigger cascades of reactions, heating up the interstellar medium and even altering the chemistry of the gas that forms stars and planets. It's a subtle but profound influence, like the ripple of a pebble dropped into a pond, spreading outward and shaping the environment in ways we're only beginning to understand. One of the most fascinating roles cosmic rays play is in regulating star formation. When these particles interact with gas clouds, they can ionize the gas, making it more resistant to gravitational collapse. This means that in regions where cosmic rays are abundant, star formation might slow down, while in quieter areas, stars can burst into life more freely. It's a delicate balance, one that helps maintain the cosmic web's dynamic equilibrium. But cosmic rays don't just influence the here and now, they also carry clues about the universe's past. By studying the paths and energies of these particles, scientists can trace their origins back to the violent events that created them. It's like piecing together a cosmic detective story, where every particle tells a tale of supernova, black holes, and the birth of galaxies. And yet, cosmic rays are just one piece of the puzzle. As powerful as they are, they share the stage with another mysterious traveler, the neutrino. These ghostly particles, nearly massless and almost impossible to detect, are the universe's silent observers passing through matter as if it weren't even there. What role do they play in the cosmic web? How do they interact with the vast structures we've explored so far? The next pattern will take us into the enigmatic world of neutrinos, where the story of the cosmic web becomes even more fascinating. Among the universe's most enigmatic travelers are neutrinos, tiny, nearly massless particles that zip through space, barely interacting with anything in their path. Often called ghost particles, neutrinos are so elusive that trillions of them pass through your body every second without you ever noticing. But don't let their invisibility fool you. These particles are cosmic detectives, carrying secrets about the universe's earliest moments and the vast structures that define the cosmic web. To understand neutrinos, imagine them as cosmic whispers, faint, fleeting, but packed with information. Born in the hearts of stars, supernova, and even the Big Bang itself, neutrinos are messengers from some of the universe's most dramatic events. Unlike light, which can be absorbed or blocked, neutrinos travel unimpeded, offering a direct line of sight to the cosmos' most hidden corners. This makes them invaluable tools for probing the cosmic web, especially in regions where other signals fade away. One of the most fascinating aspects of neutrinos is their role in the early universe. Just moments after the Big Bang, the cosmos was flooded with these particles, shaping the distribution of matter and energy in ways that would later influence the formation of galaxies and clusters. Neutrinos, with their slight but significant mass, helped create the tiny density fluctuations that gravity would later amplify into the vast filaments of the cosmic web. Think of them as the original architects laying the groundwork for the structures we see today. But neutrinos don't just belong to the past. Even now, they play a subtle yet crucial role in shaping the universe. As they stream through space, they interact with the gas and dark matter that make up the cosmic web, influencing how galaxies form and evolve. While their impact is subtle, more like a nudge than a shove, it's enough to leave a lasting mark on the universe's grand design. Detecting neutrinos is no easy feat. Because they rarely interact with matter, scientists have to build massive detectors deep underground, shielded from other cosmic noise. These detectors, like the Ice Cube Observatory in Antarctica, use vast arrays of sensors to catch the rare flashes of light that occur when a neutrino finally collides with an atom. Each detection is a triumph, a fleeting glimpse into the hidden workings of the cosmos. As we marvel at the ghostly influence of neutrinos, another cosmic phenomenon comes into focus, one that ripples through space-time itself. Gravitational waves, the echoes of cataclysmic events like colliding black holes and neutron stars, offer a new way to map the cosmic web. How do these ripples in the fabric of reality connect to the universe's largest structures? That's where we're headed next, into the dynamic interplay of gravity and space-time, where the story of the cosmic web continues to unfold. In the vast, interconnected tapestry of the cosmic web, there's a hidden force that ripples through the very fabric of reality itself, gravitational waves. These subtle distortions in space-time, first predicted by Einstein over a century ago, are not just theoretical curiosities, they're cosmic messengers, carrying secrets about the universe's most violent and energetic events. Imagine space-time as a calm lake and gravitational waves as the ripples that spread outward when a stone is tossed in. Except in this case, the stones are cataclysmic events like colliding black holes or merging neutron stars, events so powerful they send shockwaves across the cosmos. The detection of gravitational waves in 2015 marked a turning point in our understanding of the universe. For the first time, we could listen to the cosmos, picking up vibrations from events billions of light years away. These waves don't just tell us about the objects that created them, they also offer a new way to study the cosmic web. As they travel through the universe, gravitational waves interact with the vast structures of galaxies, clusters, and filaments, subtly altering their path. By analyzing these changes, scientists can map the distribution of matter in ways that light-based observations can't achieve. Take, for example, the merging of two black holes. When these titanic objects spiral into each other, they release a burst of gravitational waves that carries information about their masses, spins, and even the environment around them. In some cases, these mergers occur in regions dense with galaxies or filaments, and the waves they produce can reveal the presence of dark matter or the density of gas in those areas. It's like using sonar to map the ocean floor, except here, the ocean is the universe, and the sonar is the faint echo of colliding black holes. But gravitational waves aren't just tools for mapping the cosmic web, they also tell us about its history. Some of the earliest gravitational waves, still rippling through the universe today, were created during the Big Bang itself. These primordial waves, if detected, could reveal clues about the universe's infancy, offering a glimpse into the moment when the cosmic web first began to take shape. It's a tantalizing possibility, one that could connect the dots between the universe's birth and the sprawling network of galaxies we see today. As we continue to unravel the mysteries of gravitational waves, another cosmic phenomenon comes into focus, one that stretches the imagination even further. What if the very structure of the cosmic web was shaped by an event so rapid and dramatic that it occurred in the tiniest fraction of a second after the Big Bang? This is the story of cosmic inflation, a theory that suggests the universe expanded faster than the speed of light in its earliest moments. How did this explosive growth influence the patterns we see today? And what does it tell us about the forces that shape the cosmos? That's where we're headed next, into the realm of cosmic inflation, where the story of the cosmic web becomes even more extraordinary. The universe didn't just expand, it exploded into existence. Picture this: in the tiniest fraction of a second after the Big Bang, the cosmos underwent a dramatic growth spurt, inflating faster than the speed of light. This is cosmic inflation, a theory that not only explains the universe's staggering size, but also lays the groundwork for the cosmic web's intricate structure. During this brief but transformative moment, the universe expanded from a speck smaller than an atom to something vastly larger, all in less time than it takes to blink. This rapid expansion wasn't just about size, it was about seeding the universe with the raw materials for everything we see today. Tiny quantum fluctuations, microscopic ripples in the fabric of spacetime, were stretched to cosmic scales during inflation. These ripples became the seeds of structure, the faintest variations in density that gravity would later amplify into galaxies, clusters, and the vast filaments of the cosmic web. Think of it like blowing up a balloon with tiny dots painted on its surface. As the balloon expands, the dots spread out, their patterns preserved but magnified. Cosmic inflation did the same for the universe, imprinting its early quantum whispers onto the grand canvas of the cosmos. What's remarkable about this process is its precision. The fluctuations created during inflation were incredibly subtle, just a few parts in 100,000. Yet, these tiny imperfections were enough to set the stage for the universe's entire structure. Over billions of years, gravity pulled matter into denser regions, while the voids between them grew emptier, creating the web-like pattern we observe today. Without inflation, the universe might have remained a smooth, featureless expanse, devoid of the galaxies, stars, and planets that make it so vibrant. But inflation didn't just shape the cosmic web, it also left behind clues about its own history. The cosmic microwave background, that faint echo of the Big Bang, carries the fingerprints of these early fluctuations. By studying its patterns, scientists can reconstruct the universe's infancy, tracing the origins of the cosmic web back to those first moments of explosive growth. It's like finding a time capsule from the dawn of creation, filled with secrets about how the universe began. As we reflect on the profound impact of cosmic inflation, it's worth asking, what came next? How did the universe transition from these early seeds of structure to the rich tapestry of galaxies and clusters we see today? The answer lies in the next chapter of the cosmic web story, one where ordinary matter, the stuff we're made of, takes center stage. From the tiniest particles to the largest structures, baryonic matter plays a crucial role in shaping the universe. What secrets does it hold about the cosmic web's evolution? And how does it connect the universe's past to its present? That's where we're headed next, into the heart of the matter that makes the cosmos come alive. While the cosmic web is often thought of in terms of its vast, invisible threads of dark matter, there's another player in this cosmic drama, one that's far more familiar to us. This is baryonic matter, the ordinary stuff that makes up everything we can see and touch: stars, planets, galaxies, and even ourselves. Though it makes up less than 5% of the universe's total mass, baryonic matter is far from insignificant. It's the visible face of the cosmic web, the glittering jewels that adorn its dark, invisible scaffolding. Baryonic matter doesn't just fill the universe, it animates it. Stars shine, galaxies spin, and planets form because of this ordinary matter. But its role in the cosmic web goes even deeper. As galaxies and clusters form along the filaments of dark matter, baryonic matter flows into these structures, cooling and condensing to ignite the fires of star formation. It's the fuel that powers the cosmic web, turning abstract patterns into vibrant, living systems. Yet, baryonic matter doesn't act alone. Its movements are guided by the gravitational pull of dark matter, the unseen force that shapes the web's structure. Imagine dark matter as the skeleton of the universe and baryonic matter as the flesh that gives it form. Together, they create the intricate balance that defines the cosmic web. For instance, when gas clouds fall into the gravitational wells of dark matter filaments, they heat up, creating the glowing plasma that astronomers observe in galaxy clusters. But baryonic matter isn't just a passive participant, it also influences the cosmic web's evolution. When stars explode as supernova, they release energy and heavy elements into their surroundings, enriching the gas that will one day form new stars and planets. These cycles of birth and destruction ripple through the cosmic web, shaping its structure over billions of years. As we explore the interplay between baryonic matter and the cosmic web, it's worth asking, what happens in the spaces where matter is sparse? While baryonic matter fills the galaxies and clusters, the voids between them are nearly empty, dominated by the mysterious forces of dark energy. These cosmic deserts are more than just empty space, they're an essential part of the universe's structure. What secrets do they hold about the cosmic web's grand design? That's where we're headed next, into the quiet, mysterious realm of cosmic voids. As we journey through the cosmic web, we've marveled at the bustling galaxy clusters and the brilliant lighthouses of quasars. But now, let's turn our attention to the quiet, almost forgotten spaces in between the cosmic voids. These vast, nearly empty regions are more than just gaps in the universe. They're an essential part of its structure, shaping the cosmic web in ways that are both subtle and profound. Think of cosmic voids as the valleys between towering mountain ranges. While the peaks, galaxies, and clusters draw all the attention, it's the valleys that define the landscape. Voids make up most of the universe's volume, stretching for hundreds of millions of light years with barely a galaxy in sight. They're not just empty space, they're the yin to the cosmic web's yang, the quiet counterpoints that give the universe its balance. But how do these voids influence the cosmic web? One of their most important roles is in shaping the motion of galaxies. As galaxies within filaments are pulled toward the dense clusters, the voids act like cosmic vacuums, gently tugging matter away from the densest regions. This interplay between attraction and repulsion creates a delicate dance, where galaxies flow along the filaments like water through a network of rivers, guided by the gravitational pull of both clusters and voids. It's a cosmic balancing act where the emptiest regions play just as crucial a role as the most crowded ones. Voids also offer a unique window into the universe's evolution. Because they contain so little matter, they're less affected by the chaotic processes of star formation and galaxy collisions. This makes them pristine laboratories for studying the effects of dark energy, the mysterious force driving the universe's accelerated expansion. In the emptiness of voids, dark energy's influence is more pronounced, subtly stretching the fabric of space and shaping the cosmic web on the grandest scales. Yet, for all their significance, cosmic voids remain one of the least understood aspects of the universe. Their emptiness makes them challenging to study, but it's precisely this emptiness that holds clues to the universe's past and future. What can these quiet spaces tell us about the forces that govern the cosmos, and how do they connect to the filaments that weave through them? That brings us to the next pattern in the cosmic web, the galaxy filaments themselves. These immense threads of matter stretching across the universe are the highways along which galaxies travel, the bridges that connect clusters and voids. What secrets do they hold about the universe's structure, and how do they fit into the grand design of the cosmic web? The next pattern will take us there, into the heart of these cosmic threads, where the story of the universe continues to unfold. Now let's zoom in on one of the most striking features of the cosmic web galaxy filaments. These slender, thread-like structures are the highways of the universe, weaving through the vast expanse of space and connecting galaxy clusters like beads on a cosmic string. Imagine the cosmic web as a grand tapestry, with filaments as the delicate threads that hold everything together. Among the most remarkable of these filaments is the Pisces-Cetus Supercluster complex, a sprawling network of galaxies that stretches over 1 billion light-years, connecting some of the largest structures in the universe. Galaxy filaments aren't just cosmic decorations, they're the backbone of the universe's large-scale structure. They act as conduits for matter, channeling gas and galaxies into the dense clusters where stars and planets are born. This flow of material is crucial for galaxy formation, as it provides the fuel needed to ignite new stars and sustain the growth of galaxies over billions of years. Without these filaments, the cosmic web would collapse into disconnected islands, and the universe as we know it would look entirely different. The Pisces-Cetus Supercluster complex is a perfect example of this process in action. Spanning an enormous region of space, it links multiple galaxy clusters, including the Virgo cluster and the Perseus-Pisces supercluster. Along its length, galaxies move like cars on a freeway, drawn by gravity toward the densest regions where they'll eventually merge and evolve. It's a dynamic, ever-changing system where the interplay of gravity and motion shapes the destiny of galaxies. But galaxy filaments do more than just connect clusters, they also play a role in the universe's evolution. As galaxies move along these filaments, they interact with one another, triggering bursts of star formation and even galactic collisions. These interactions can reshape entire galaxies, leaving behind trails of gas and stars that tell the story of their journey through the cosmic web. It's a process that's both chaotic and beautiful, a testament to the delicate balance of forces that govern the universe. As we marvel at the intricate network of galaxy filaments, it's worth asking, what holds this cosmic web together? While gravity plays a starring role, there's another, more mysterious force at work, one that's shaping the universe on the grandest scales. This is dark energy, the enigmatic force driving the universe's accelerated expansion. How does this invisible power influence the cosmic web, and what secrets does it hold about the universe's fate? That's where we're headed next, into the shadowy realm of dark energy, where the story of the cosmic web takes a surprising turn. As we delve deeper into the cosmic web, we encounter a force so mysterious and powerful that it shapes the very fabric of the universe: dark energy. This enigmatic force, which makes up roughly 70% of the universe's total energy, is the driving engine behind the accelerated expansion of the cosmos. Unlike gravity, which pulls matter together, dark energy works in the opposite direction, pushing space itself apart at an ever-increasing rate. It's as if the universe is stretching, not just expanding, but accelerating into an ever-widening expanse. Dark energy's influence on the cosmic web is profound. While gravity weaves the filaments and clusters of galaxies into the intricate patterns we see, dark energy acts as a counterbalance, stretching the voids between them. Picture the cosmic web as a rubber sheet. Gravity pulls the sheet inward, creating dips and folds where galaxies gather, while dark energy stretches the sheet outward, expanding the empty spaces. This interplay between attraction and repulsion shapes the universe's large-scale structure, determining how galaxies move and where they cluster. One of the most fascinating effects of dark energy is its impact on galaxy motion. As the universe expands, galaxies within filaments are pulled toward dense clusters by gravity, but dark energy is subtly working against this motion. Over billions of years, this tug-of-war slows the flow of galaxies into clusters, leaving the cosmic web with a delicate, almost fragile structure. The farther apart galaxies are, the more dark energy dominates, pushing them apart and reshaping the cosmic web on the grandest scales. Yet, for all its power, dark energy remains one of the greatest mysteries in modern science. We don't know what it is or how it works, only that its presence is felt everywhere, from the tiniest voids to the largest clusters. Some scientists believe dark energy could be a property of space itself, a kind of cosmic pressure that grows stronger as the universe expands. Others suggest it might be connected to entirely new physics, a clue to forces we've yet to discover. As we ponder the mysteries of dark energy, another cosmic phenomenon comes into focus, one that illuminates the early stages of the universe's evolution. Just as dark energy shapes the cosmic web today, cosmic reionization played a crucial role in shaping it in the past. This process, which occurred billions of years ago, marked the universe's transition from a dark, opaque fog to a clear, luminous expanse filled with stars and galaxies. What role did reionization play in the cosmic web's formation, and how does it connect to the universe we see today? That's where we're headed next, into the dawn of light and structure, where the story of the cosmic web continues to unfold. Long before the cosmic web became the intricate network of galaxies and filaments we see today, the universe was a dark, murky place, shrouded in a fog of neutral hydrogen gas. But then, something extraordinary happened, a cosmic dawn that illuminated the universe and set the stage for everything that followed. This transformative era is known as cosmic reionization, a pivotal moment in the universe's history when the first stars and galaxies began to shine, lighting up the cosmos and reshaping its structure. Imagine the early universe as a vast, dark forest filled with dense fog. For hundreds of millions of years after the Big Bang, the universe was opaque, with light unable to travel freely. But as the first stars ignited and galaxies formed, their intense radiation began to ionize the surrounding hydrogen gas, stripping away the fog and making the universe transparent. It's like the sun rising over that dark forest, burning away the mist and revealing the landscape for the first time. This process didn't happen all at once. It unfolded over hundreds of millions of years as pockets of ionized gas expanded and merged, creating bubbles of clarity in the cosmic fog. These bubbles eventually grew large enough to overlap, connecting the first galaxies and forming the earliest threads of the cosmic web. Cosmic reionization wasn't just about making the universe transparent. It was about laying the groundwork for the large-scale structure we see today. The impact of reionization on the cosmic web is profound. As the first galaxies ionized their surroundings, they altered the density and temperature of the gas, influencing how matter flowed and clustered. This process helped shape the filaments and voids that define the cosmic web, setting the stage for the formation of galaxy clusters and superclusters. Without reionization, the universe might have remained a dark, featureless expanse, with galaxies unable to form and evolve as they have. But reionization wasn't just a one-time event. It left behind clues that astronomers are still uncovering today. By studying the light from distant quasars and galaxies, scientists can trace the history of reionization, piecing together how the universe transitioned from darkness to light. It's like finding ancient footprints in the sand, revealing the steps that led to the universe we know today. As we reflect on this cosmic dawn, it's worth asking, what came next? How did the first galaxies, those pioneers of the universe, continue to shape the cosmic web? The answer lies in the next chapter of this story, one where the earliest galaxies take center stage, weaving the threads of the cosmic web and setting the universe on a path that would lead to galaxies like our own. What role did these ancient galaxies play in the grand design of the cosmos? And how did they lay the foundation for the universe we see today? That's where we're headed next, into the heart of the first galaxies and their enduring legacy. As the universe emerged from its dark, foggy beginnings, the first galaxies began to take shape, igniting a cosmic revolution that would forever change the fabric of space. These early galaxies, born within the slender filaments of the cosmic web, were more than just collections of stars. They were the pioneers of light, the architects of structure, and the seeds of everything we see today. Picture the cosmic web as a vast, invisible scaffolding, with filaments stretching across the void like the veins of the universe. Within these filaments, gas and dark matter began to clump together, pulled by gravity into dense knots where the first galaxies could form. These galaxies weren't like the ones we see today. They were smaller, hotter, and far more chaotic, bursting with the energy of young stars and the glow of ionized gas. As they grew, their intense radiation began to clear away the surrounding hydrogen fog, carving out bubbles of transparency in the universe's once opaque expanse. It's as if these galaxies were the first sparks of light in a vast, dark forest, slowly burning away the mist to reveal the landscape beneath. But the role of these early galaxies went beyond illumination. They were also the building blocks of the cosmic web itself. As they formed and grew, they pulled in more gas and dark matter, strengthening the filaments that connected them. Over time, these filaments became the highways of the universe, guiding the flow of matter and shaping the distribution of galaxies on the grandest scales. The first galaxies didn't just light up the universe, they wove its structure, laying the foundation for the cosmic web we observe today. What's truly remarkable is how these early galaxies influenced the universe's evolution. Their intense radiation didn't just ionize gas, it also heated it, slowing the formation of new stars and regulating the growth of galaxies. This delicate balance between creation and regulation ensured that the cosmic web didn't collapse under its own weight, but instead grew into the intricate, balanced structure we see today. As we marvel at the legacy of these first galaxies, it's worth considering what came next. The cosmic dawn, that era when the universe transitioned from darkness to light, wasn't just a moment of illumination. It was a turning point, a cosmic awakening that set the stage for the universe's future. What role did this cosmic dawn play in shaping the cosmic web? And how did it connect the first galaxies to the sprawling networks of clusters and filaments we see today? That's where we're headed next, into the heart of the cosmic dawn, where the story of the universe's transformation continues to unfold. The cosmic dawn, what a name for a moment that changed everything. Imagine the universe as a dark, silent theater waiting for the first act to begin. Then, suddenly, the curtains part and light floods the stage. This is the cosmic dawn, the era when the first stars and galaxies ignited, piercing the darkness and illuminating the cosmos for the very first time. It wasn't just a moment of brightness, it was the beginning of structure, the spark that set the universe on a path toward the intricate cosmic web we see today. Before this dawn, the universe was a sea of neutral hydrogen gas, thick and opaque like a dense fog. Light couldn't travel far, and the cosmos was shrouded in darkness. But as the first stars burst into life, their intense radiation began to ionize the surrounding gas, stripping electrons from atoms and clearing the fog. Picture it like the sun breaking through a cloudy sky, transforming the world from gray to vibrant color. These early stars and galaxies didn't just light up the universe, they sculpted it. The cosmic dawn wasn't just a cosmic light show, it was a turning point in the universe's evolution. As those first galaxies formed, they pulled in gas and dark matter along the filaments of the cosmic web, strengthening these threads and creating the scaffolding for future structures. It's like watching a city grow. The first buildings define the streets, which then guide the growth of neighborhoods. Similarly, the cosmic dawn laid the foundation for the vast networks of galaxies and clusters we see today. But here's where it gets even more fascinating. The light from those early galaxies didn't just clear the fog, it also heated the gas, slowing the formation of new stars and regulating the growth of galaxies. This delicate balance ensured that the cosmic web didn't collapse under its own gravity, but instead grew into the intricate, balanced structure we observe today. Without the cosmic dawn, the universe might have remained a dark, featureless void, with galaxies unable to form and evolve as they have. As we marvel at this pivotal era, it's worth considering what came next. The cosmic dawn wasn't just a moment of illumination, it was the first step in a journey that continues to shape the universe. The cosmic web, born from those early threads of gas and light, is still evolving, still weaving new patterns into the fabric of space. And that brings us to the next pattern in our exploration, the role of the cosmic web in the universe's future. How will this vast network of galaxies and filaments continue to shape the cosmos? What forces will guide its evolution, and what secrets will it reveal about the universe's ultimate fate? The answers lie ahead in the next chapter of this cosmic story. The cosmic web, with its intricate threads of galaxies and voids, isn't just a static map of the universe, it's a living, evolving entity. As the universe continues to expand, driven by the relentless force of dark energy, the cosmic web is changing in ways that will shape the cosmos for billions of years to come. Picture the universe as a tapestry, slowly stretching and thinning as dark energy pulls its threads apart. The galaxies we see today, once clustered tightly along the filaments, will drift farther and farther apart, their connections weakening as the voids between them grow ever larger. Dark energy, that mysterious force pushing the universe's expansion, plays a starring role in this cosmic drama. While gravity works to pull galaxies together, dark energy is the counterbalance, stretching space itself and accelerating the universe's growth. Over time, this tug-of-war will tip in dark energy's favor. The filaments of the cosmic web, once vibrant highways of matter, will stretch and thin, their once dense clusters becoming isolated islands in an ever-expanding sea of emptiness. But what does this mean for the universe's future? In the distant eons to come, the cosmic web will become a sparser, more fragmented structure. Galaxies within clusters will eventually merge, creating supergalaxies that dominate their local regions. Meanwhile, the voids between these clusters will grow so vast that light from distant galaxies may never reach us, leaving future civilizations, if they exist, with a night sky far emptier than our own. It's a future that's both awe-inspiring and humbling, a reminder of the impermanence of even the grandest cosmic structures. Yet, even as the cosmic web stretches and fades, its story is far from over. The forces that shaped it, gravity, dark matter, and dark energy, will continue to shape the universe, albeit in ways we're only beginning to understand. And as we ponder the ultimate fate of the cosmos, another question arises. What role does the cosmic web play in the search for life beyond Earth? Could its vast filaments and voids hold clues to where life might exist or even thrive in the universe? That brings us to the next pattern in our exploration, the cosmic web as a potential map for finding extraterrestrial life. Could its structure guide us to the most promising corners of the cosmos? And what secrets might it reveal about the possibility of life elsewhere in the universe? The answers lie ahead in the final chapter of this cosmic journey. As we gaze out at the cosmos, one question looms larger than any other. Are we alone? The cosmic web, with its intricate filaments and vast voids, might hold the key to answering this age-old mystery. Far from being a random arrangement of galaxies, this grand structure could act as a cosmic roadmap, guiding us to the most promising regions where life might exist or even thrive. Think of the cosmic web as a sprawling city with bustling neighborhoods and quiet suburbs. The dense clusters of galaxies are like urban centers, teeming with activity but often too chaotic for life to take hold. On the other hand, the filaments, those slender threads connecting the clusters, might be the cosmic equivalent of quiet, well-balanced neighborhoods. Here, conditions could be just right for planets to form and life to emerge. These filaments offer a stable environment, with enough resources from surrounding gas clouds to fuel star and planet formation, yet not so crowded that gravitational interactions would disrupt the delicate balance needed for life. But what about the voids? These vast, nearly empty regions might seem like cosmic dead zones, but they could play a surprising role in the search for life. While they lack the density of galaxies found in filaments and clusters, voids might contain isolated galaxies or even rogue planets drifting through the darkness. In these quiet corners of the universe, life could evolve undisturbed by the gravitational chaos of denser regions. Imagine a lone planet orbiting a star in the middle of a void, shielded from cosmic hazards like supernova or black holes, a perfect haven for life to flourish. Some scientists even speculate that the cosmic web structure could create galactic oases, regions where the conditions for life are especially favorable. For example, galaxies located near the intersections of filaments might benefit from a steady flow of gas and resources, fostering the formation of habitable planets. These oases could be the universe's most promising targets in our search for extraterrestrial life. As we ponder the cosmic web's potential to guide our search for life, another tantalizing possibility emerges. Could this vast network also hold clues to the existence of other universes? The cosmic web isn't just a structure within our universe, it might be a window into something even grander, the multiverse. How does the cosmic web connect to the idea of multiple universes? And what secrets might it reveal about the nature of reality itself? That's where we're headed next, into the final pattern of our cosmic journey, where the boundaries of our understanding are pushed to their limits. The cosmic web, with its intricate filaments and vast voids, might not just be a map of our universe, it could be a window into something even grander, the multiverse. Imagine the cosmic web as a single thread in an infinite tapestry, one of countless universes woven together in a higher dimensional fabric. This idea, while mind-bending, is one of the most tantalizing theories in modern cosmology. Could the patterns we see in the cosmic web hint at the existence of other universes, each with its own laws of physics and unique structures? Some scientists suggest that the cosmic web's architecture might reflect the influence of a multiverse. Think of it like this: if our universe is a bubble in a vast cosmic ocean, other universes could be nearby bubbles, each expanding and interacting in ways we can't directly observe. These neighboring universes might leave subtle imprints on our own, shaping the distribution of galaxies and the patterns of the cosmic web. It's as if the cosmic web isn't just a product of our universe's history, it's a ripple from a much larger hidden reality. One compelling theory is that the cosmic web's largest structures, like superclusters and voids, could be the echoes of collisions between our universe and others in the multiverse. Picture two soap bubbles gently brushing against each other. The point of contact might leave a faint mark, a distortion in the fabric of space that influences how matter clusters and flows. In the same way, interactions between universes could create anomalies in the cosmic web, subtle clues that point to a reality far beyond our own. But how do we search for evidence of a multiverse within the cosmic web? One approach is to study the cosmic microwave background, the faint afterglow of the Big Bang. Tiny irregularities in this ancient light might hold hints of interactions with other universes. Another possibility lies in the distribution of galaxies and voids. If the cosmic web's patterns show unexpected symmetries or anomalies, they could be fingerprints of a multiverse, subtle signs that our universe is part of something infinitely larger. This concept isn't just a flight of fancy. It's grounded in cutting-edge theories like string theory and brane cosmology, which propose that our universe is just one of many existing in higher dimensions. While these ideas are still speculative, they challenge us to rethink our place in the cosmos. The cosmic web, far from being a static map, might be a living, evolving record of our universe's connection to a multiverse beyond our imagination. As we reflect on these profound possibilities, let's return to the central theme of our journey, the cosmic web as a guide to understanding the universe's deepest mysteries. From the birth of the first galaxies to the enigmatic forces shaping its future, the cosmic web is more than a structure. It's a story, one that ties together the past, present, and potential futures of the cosmos. Whether it reveals the existence of other universes or simply deepens our understanding of our own, the cosmic web reminds us that the universe is far stranger and more interconnected than we ever imagined. And so, as we conclude this exploration of the cosmos's 28 enigmatic patterns, remember this: the cosmic web isn't just a map, it's an invitation to wonder, to explore, and to discover the secrets that lie beyond the stars. The universe is waiting and its mysteries are calling. What will we find next? Only time and the cosmic web will tell. As we reach the end of our journey through the cosmic web, it's time to reflect on the 28 enigmatic patterns that have unveiled the universe's deepest secrets. From the colossal Great Wall of Galaxies to the haunting emptiness of the Boots Void, from the blazing brilliance of quasars to the invisible threads of dark matter, each pattern has revealed a piece of the cosmos' grand puzzle. These structures are more than just scientific curiosities. They're the fingerprints of the universe's history, the echoes of its birth, and the blueprints of its future. These patterns remind us that the universe is far more than a collection of stars and galaxies. It's a dynamic, interconnected network shaped by forces both seen and unseen. The cosmic web is a living testament to the universe's complexity, a tapestry woven from the threads of gravity, dark energy, and the raw materials of creation. Each time we uncover a new pattern, we're not just learning about the cosmos, we're learning about ourselves, our place in the grand scheme of things, and the profound connections that bind us to the universe. Think about it: every atom in your body, every star in the sky, every galaxy in the cosmic web, is part of the same story, a story that began with the Big Bang and continues to unfold with every passing moment. The 28 patterns we've explored are chapters in that story, each one deepening our understanding of how the universe works and inspiring us to ask even bigger questions. What lies beyond the cosmic web? Are there other universes out there, each with its own patterns and secrets? And what role do we, as conscious beings, play in this vast, unfolding narrative? As we stand on the edge of discovery, it's clear that the cosmic web is more than a scientific concept. It's an invitation to explore, to wonder, and to marvel at the infinite mysteries of the universe. Whether you're a seasoned stargazer or someone just beginning to look up at the night sky, the cosmic web offers something for everyone, a chance to connect with the cosmos and to see the universe in a whole new light. So, what do you think? Which of these 28 patterns resonated with you the most? Do you find yourself drawn to the immense structures like the Hercules-Corona Borealis Great Wall? Or do the quieter mysteries of cosmic voids and dark matter intrigue you more? Whatever your thoughts, we'd love to hear them. Share your reflections in the comments below, and don't forget to subscribe for more journeys into the wonders of the cosmos. The universe is vast and its mysteries are endless, but with every discovery, every pattern we uncover, we take one step closer to understanding our place in the grand cosmic dance. So keep looking up, keep wondering, and keep exploring, because the universe is waiting and its secrets are calling. What will we discover next? The answer is out there, somewhere